Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 11, that is cyber physical layers in distribution system. In the last class we started about the non-ideal communication mediums, what are their characteristics, how we can model the noise, packet loss and erroneous data transfer. So, we will continue that non-idealities, how to model them, and we will see few more non-ideal events. So, we have started with the additive noise, right, but we have seen that the additive noise, how they have modeled, that is mostly of the analog type. We took a probability density function, that is a Gaussian distribution, right. You have a Gaussian distribution. So, that is a continuous function. There is a continuous function, but we have seen that in the smart grid digital communication methods are mostly adapted to transmit the data. So, how this will be converted to a digital platform? So, that is for the end to end supply in the PLC and the fiber. So, that is done, this noise is not added as an analog value, that is normally added as a digital value, and that will the noise impacted transmission message by doing the bit flipping. What is bit flipping? Bit flipping means, let us say you are sending this data 101100, that is your original signal. The bit flipping will say that noise has been added and now it has been converted to 10, let us say 0100. So, this 1 has now changed to or flipped to 0. That can be reversed, 0 also can be flipped to 1. That is, one or multiple positions of that bits can be flipped. So, that has been added as a noise in case of a digital communication platform. So, the digital communication strategies use modulators and demodulators at either side of the communication medium for analog to digital and digital to analog conversion, that we have already seen, that you have channel encoders, then you have channel decoders, okay, or source encoder and source decoder. So, here you have a modulator and you have a demodulator, where here you are sending actually a 10010101 pulse, okay, and that has been added. Let us say here one noise has been added. So, because of that, if you are sending it here like this, that 0011, then you have 00, like this kind of a pulse for a time interval, and because of this noise addition it has become like this 00, then 1, then again 0, 1, sorry, this will be 1, then 0, then again 0, 0. So, you are experiencing a bit flip in this position because of the additive noise. Okay. Then you are demodulating it and you will get something else value. You send something else, if you convert it to a decimal value, that is something else value, and if you convert it to this to decimal value, you will get something else value. So, that causes your data deformation or effect of the noise with the data. So, generally single carrier modulations like phase shift keying or multi-carrier demodulation schemes like orthogonal frequency division multiplexings are normally implemented at the modulation and the demodulation purposes. We will see what is the most used, that is the binary phase shift keying or communication scheme, which is generally adopted in the power system. So, general block diagram for the BPSK digital communication is this, which is the same. Okay. Now, the modulator transmits the signal, whereas the demodulator receives the transmitted data. The noise is added in the channel after modulation and that causes the bit flipping, that what I just told. BER quantifies the probability of a bit being received incorrectly or flipped due to noise interference or other impairments in the transmission channel. What is BER? This is called bit error rate. That is a probability, that signifies a probability that if you are sending a trains of bits, then what is the probability that a bit will be flipped. Okay. This is the probability of it. So, normally this is the probability quantity. Okay, it signifies a probability that it will be flipped due to noise. It is calculated by dividing the number of bit errors flipped bits received by the total number of bits transmitted. That means, let us say you are sending 6 bits and let us say only 2 bits or 4, let us say 3 bits has been flipped, then there is a probability, that means the bit error rate for transmitting that data is 3 by 6 equals to, that means P of BER is equals to half, that means 50%. Okay. A low BER signifies good data transmission, that is obvious. That means if that is reduced, like you have, let us say only one bit data are flipped, then that is 1 by 6 probability. So, that is good, there is only one bit flipping is possible. If there is more like 4, 5, then that means your error, getting error in the data is more. So, that is bad. Now, for transmitting a message, both bits 0 and 1 are equally to be transmitted, because there are only one possibility. So, their probability will be equal. So, that is 50% probability, 0.5. So, probability of 0 or probability of 1 is half. Now, if ST is the transmitted signal, that is the actual transmitted signal, say plus A for bit 1 and minus A for bit 0, and NT is the noise, then the actual transmitted signal is given by RT equals to ST plus NT, that we have seen whenever it is an additive noise. So, that noise will be directly added with the your signal. So, that means it is a binary addition we are doing. Yeah, and that is a binary addition, that means that we know 1 plus 1 equals to 0, 1 0. So, some extra changes in the bits or in the your sending data binary digit is happening. So, when both bits are equally likely, choosing 0 as the threshold minimize the probability of error, that is called the maximum likelihood or Bayesian detection theory. Okay. So, therefore, obeying the 0 threshold, if you have a 0 threshold, if you set by this by Bayesian detection. So, if RT is greater than 0, that means if it is more than the threshold, then decide the bit will be 1. Okay. And if the RT is less than 0, then decide the bit to be 0. So, depending upon the threshold, what threshold value you are setting, generally it is set to 0. So, if you set that and then you see what values you are getting. Okay. If the value is greater than 0 with the noise, then you can set it at 1, and if it is less than 0, then you set 0. So, if a noise, let us say you have some value and noise is added, that value is already greater than 0. So, it is already 1, okay. And with that noise is added, so that is further enhanced it. So, that will make the it is keep it at 1. So, you will not experience any bit flipping here. But let us say the noise is additive and it is like a negative kind of value added, minus value is added. So, what will happen? That will reduce the value of that actual signal, the strength or power of that actual signal. Then if it is goes below 0 because of that, then what will happen? Then that 1 will be transmitted 1 will be converted to 0. So, that will cause a bit flipping, and that is vice versa, the opposite is also true. So, now for Gaussian probability distribution function, which is normally we considered for all our AAC noise, NLI noise or PLC noises, the probability of bit error rate for a communication channel you can calculate with this equation, which is coming out to be half of error function. This is the error function, mathematical error function. Normally it is denoted by this equation, integration equation, root over of gamma by 2, where gamma is your signal to noise ratio, and Pb, if the Pb is the transmitted power of the signal of the transmitted power and N0 is the noise power density, then gamma is Pb by N0. Okay, got it? Now, we have seen that for Gaussian noise power, when the noise power is modeled as a Gaussian or it is a normal distribution noise. So, at that time the noise power is same as its variance value, that is theoretically proved. So, your signal to noise ratio is Pb by sigma square. Now, put that value to this equation and you will get your PBR or probability of the bit error rate, that is half of error function root over of Pb by 2 sigma square. Now, for PLC we have seen that is a Gaussian mixture noise. So, at that time if we put this value to the noise model of the PLC, the additive noise model, then the overall equation looks like this, where this is your overall your standard deviation or variance value of the overall PLC noise. This includes your background noise and also your impulse noise. So, we have seen that if your I equals to 0, that is your background noise, and depending upon the I value, that 1, 2, 3, then number of impulses will increase. So, this is your bit error rate, which is depending upon your only standard deviation or the variance value of the noise level. Similarly, for optical fiber also, that is a Gaussian model we have done for the NLI and AAC, and if we signify it or if we model it, then that is also takes the form like this. It is the same formula, only here you have the summation, because you need to add all the effect of all the impulses, but here it is only 1. So, for the above equations, the bit error rate probability is calculated by choosing proper values of the noise power and the variance. So, if you change the noise power and the variance, then depending upon that you will get your bit error rate probability. So, we will see how we can do it. So, vary the optical fiber noises as follow: vary the PV value from minus 100 dBm to minus 20 dBm, that is we are reducing it to this, and this is your BER. Okay. So, this for the PLC and the fiber noise model. This is for the PLC, these two, the first two, and the last one is for, this is for PLC, this is for PLC, and this is for optical fiber. Okay. So, we can see that when you increase the PB from minus 100 to minus 20, with that your bit error rate probability will fall down. That means, if your signal, this PB is what? This PB we have seen before as well. What is PB? PB is the power transmitted with the signal, that is your signal power strength or signal strength. So, if your signal strength is increasing, okay, with the same noise level, that is your standard deviation of that noise, with that your bit error rate probability will reduce. But if your signal strength is very small, so it says that for a very low power signal you can see substantial increase in the noise level or the bit error rate probability. So, that is the case for even if you increase the number of, if that impulse is also added, this is only for the background noise. If you added the impulse, then also you can see the same effect, and also for optical fiber you can see the same effect. So, if your signal is not that much strong, that means whatever sending, if it is not a strong signal, so at that time even a small noise value or a very minimal amount of noise value can create a very high of bit error rate probability. That means, it can goes up to, you can see it is close to 1. That means, if it is a minus 100 dB strength of signal, you are sending power of that signal. So, at that time you will get completely erroneous data. That means, entirely opposite data will reach to the receiving end. That is the highest probability, that is the probability of 1. So, that means, always we have to keep to send the strong signals. Okay. Now, the last modeling, that is a delay, that is also our one more concern. So, what is communication delay? Is defined as a time lapse between the sending of a message at the source and the receiving of the message at the destination. There is a time gap, you are sending it now and when you are receiving. So, these two time gaps will signify your time delay or the communication delay. It is a measured from end to end between the two applications running at the source and the destination system. That means, when you are sending, just generated the message, from there when that message has been reached to the receiving end and they started processing it, that is called your total communication delay. So, the end to end delay is the sum of the time pieces spent by the message during its processing and transmission at every traverse node. So, if this is your sender, like you have a sensor at your transformer, let the thermal sensor is there to measure the oil temperature, and that data you need to fetch at the control center. So, that data, when it is sending or it is sensing that temperature, and from there it is taking multiple layers of the communication to reach to the finally to your control center. So, this total entire journey from that sensing to the processing, how much time it elapsed, that will tell you the total communication delay. The source device incurs some delay due to format of the message. For transmission, that it will process after sending the thermal one, it has to convert it to the analog, then analog to digital, then it will digital to some optical light sources values, then it will send it, right. So, that is taking some time. Each intermediate forwarding node adds an extra delay to process and relay the message. If it is a very long distance transmission lines, you cannot put a long line or a medium. We have to put few routers or hops, or you can say nodes, communication nodes, where your communication channel will end and then another will start. So, every device will have some communication delay or processing time. So, if you add those processing time, then you will get that is also added with the delay properties. And the destination device spends additional time to decode the message and present it to the application program. So, you send it to the receiver, it is received, after that it will decode it, obviously it will filter out all the masking data or redundant data, then get the actual information, and from there the actual it will be sent to the application program. So, from sensing the data to sending into the actual algorithm what it will be used, in between that how much time is spent to process it, pre-process it, post-process it, all these things are added and compiled together, and that will give you the total communication delay time. Got it? So, what are the components for communication delay? You have first data acquisition delay, time lag between an electrical event and its digitized measurement captured by the embedded system. So, first for collecting the data you have some few millisecond or microsecond time delay. Then packet processing delay, delay added as packets are encapsulated, inspected or modified across protocol layers in the network. So, whenever you take it as an Wi-Fi, then convert it to the ZigBee, then convert it to the Ethernet, then you say go to the optical fiber, then let us say you go to the PLC. So, every time it is this same data packet is changing the nature depending upon the communication medium, and it has to change itself to make it more compatible. So, that packet processing delay is will be added. Then packet transmission delay, time taken to transmit a complete data from across each link, including error checking and forwarding. Okay. Then every medium also takes some time. Medium access delay, wait time experienced by the nodes competing for access to a shared communication medium. As I have told in the last class as well, if you do not have a dedicated communication platform, then what you will use? You will use the shared platform, what is the actual communication infrastructure of the city has, of the internet communication or cellular communication it has. So, the power network has to take the share from it. So, if already your communication network is overburdened, so many people are talking by phone, so that means your cellular network is already congested. So, at that time you are trying to enter into that communication medium. So, what will happen? So, at that time you will not get time, you will not get access to that medium. So, then you have to wait for your time. Okay. So, that is called your medium access delay. Event responding delay, time consumed in analyzing an event and initiating a control action. That means sending a breaker trip command. That means you got the data, you process it. Now, to do that event, like to respond to that event, every machine takes some time of the processing. So, that is called your event responding delay. Now, we will see how we can model the PLC delay in the mathematical form. So, propagation delays in PLC are dependent on its physical models and as well as stochastic congestion in the power line. Obviously, like if physical delay means that is the depends upon the length of the your PLC or the power line, and the stochastic delay because if you send more power, so you are taking the more bandwidth of that, or you are using more data flow in the communication power line. That means you are using the more bandwidth. So, at that time your that is a stochastic one. So, at time which time how many data you are sending, that is not fixed. So, that is an uncertain event. The random communication delay in PLC are considered to follow a hybrid probability distribution. So, combining this physical delay and your stochastic delay, normally we model the PLC delay as a hybrid probability distribution considering both physical and the congestion delays. And what is this hybrid? This is actually a log normal, gamma and a Rician distribution. Adding them together and it looks like this equation. This alpha, beta, gamma are your weights for individual probability density function, and this is your log normal, this is your gamma, this is your Rician distribution. So, this is the actual distribution functions. If you add them together with the alpha, beta, gamma multiplied with it, then you will get your actual probability density function for your PLC delay. So, this is your standard deviation and log normal, mean and standard deviation. These are shape and scale parameters for gamma distribution P and Q, and I0, S and R are the Bessel function of the first kind and non-centrality parameter and scale parameter of the Rician function. Okay. Then for optical delay, optical fiber delay. So, optical fiber delay is also physical and the stochastic. So, the physical delay that is a deterministic delay for optical fiber, because it depends upon the length of the communication line or the optical fiber and the speed of the message or speed of that wave, communication wave in that medium. So, generally in optical fiber the speed of the wave is the speed of the light, equals to speed of the light. So, generally it is also known as the propagation delay and it is calculated by this. This is your length of the communication medium and this is your speed of light, this is 2 into 10 to the power 8 meter per second. Now, for stochastic delay is caused due to internet congestion and router processing, because generally for the optical fiber that is not a dedicated communication infrastructure for the power system, it is the internet connection or internet infrastructure which is normally used by the power operators. So, at that time you have an internet, because internet is already having so many data flow, it is already overburdened with the data. So, that internet congestion is there, and as every place you have some routers and hops, so that will have some processing time. So, if you add them together, then you will get your total stochastic delay for the optical fiber. So, internet congestion delay follows the exponential distribution and the processing delay due to the routers estimated with the Gaussian distribution. So, with this if you add them, then you will get the total probability density function. Okay. This is your router delay plus your internet congestion with the convolution of your router delay will give you the total stochastic end-to-end delay. So, A is the probability of non-occurrence of internet congestion. So, if the internet congestion is there, then obviously the router congestion, router processing is obviously delayed. So, that will be correlated with each other. So, router delay is already there, that you cannot avoid, but with that you will get an extra delay that will be caused by internet congestion, and that internet congestion is again dependent upon how much delay you are incurring at the router. So, that is why this convolution operation you will see at the for denoting the your internet congestion delay. So, that is the total internet congestion and this is for the router delay alone. Okay. Now, incorporating the delay equations, if you incorporate the entire your delay equation, stochastic delay equation and simplify them, then you will get this equations with the error function. Okay. Here is your gamma is this one and this is the total error or delay function, delay values from this optical fiber is given by this equation. So, what are the communication delay standards for power system generally followed? Generally IEEE and IEC standardize the acceptable delay in the power system. So, IEEE 1646 and IEC 61850 are the two standards which are generally followed by the smart grid network. So, you can see for IEEE 1646 there are protection information must be if it is inside the substation, that has to be reached by 4 millisecond. If it is coming from outside the substation, then it has to be reached by 8 to 12 millisecond. Depending upon the monitoring and control 16 millisecond and 1 second, operation and maintenance information 1 second to 10 second, text, processed data, program file, image. So, everything has a standardized delay values, you cannot go beyond that. If you go beyond that, then you say your system is not standardized or your communication topology whatever you are designing, that is not standardized. So, your operation, like if your protection information is coming from the substation or from the area, let us say at 20 millisecond, that means you already missed your train, you missed your protection equipment to operate. So, your system will collapse, your fault current will persist and after that cascading failure you will see and your system will collapse. Similarly, for IEC 61850 you can see that message requiring immediate action at receiving IEDs, that means the protection one that will be within 3 millisecond to or 10 millisecond and 20 millisecond to 100 millisecond. Similarly, other values are also there which has been standardized by the IEC 61850. So, with this I will end today's lecture and we will continue with some case studies with the actual cyber physical co-simulation platform in the next class. Thank you.